Section 6.1, Radical Expressions and Functions. When a number is multiplied by itself, we say the number is squared. Often we need to know what number is squared in order to produce some value a. If such a number can be found, we call that number a square root of a. So let's make a quick list. We know some squares already. Take numbers like 1 times 1. If it's being multiplied by itself twice, we can write it as 1 squared, right? 1 squared is 1. 2 squared, 2 times 2, we get 4. 3 squared, 3 times 3, we get 9. 4 squared, 4 times 4, we get 16, and so on. This is what we're going to work with in this section. For radicals, think of it as working in the opposite direction. So we're going to be trying to find these numbers who are being squared. Moving forward, square root. The number c is a square root of a if c squared equals a. Just like here. For example, consider this 4 squared equals 16. The square root of 16 equals 4, since 4 squared equals 16. So in other words, we're working backwards. Roots. Every positive real number has two real numbered square roots. The number 0 just has one square root, 0 and itself. Negative numbers do not have real numbered square roots. And for most questions, we want real numbers. So keep that in mind as we work through this section. Quick example. 16 has negative 4 and 4 as square roots because negative 4 squared is 16. Since negative 4 times negative 4, a negative times a negative is positive, we get positive 16. And 4 squared is 16. 4 times 4 equals 16. Negative 9 does not have a real number square root because there's no real number for c for which c squared equals negative 9. So think about it. What two numbers can we multiply to get 9? 3 and 3, right? But I can't think of two numbers where my answer is negative 9 because these two numbers need to be the same, right? So if they're both negative, my answer will result in positive. And if they're both positive, my answer will result in positive again. So there's no real situation where I have this number squared, so a single number squared, to give us a negative. It's never negative. Moving forward. Principal square root. The principal square root of a non-negative number is its non-negative square root. The symbol, the square root, represents the principal square root of a. To name the negative square root of a, we can write the negative outside. And when we do this, we're essentially multiplying by the negative and then applying a square root. In other words, it is incorrect to take the square root of a negative. As you continue with your education mathematics, we learn how to work with such situation, but not yet. In case you remember from high school, this is where we work with imaginary numbers. Not to say that there's fake numbers, real numbers, and imaginary numbers. That's not the case. That's just what they're called. Let's do an example. Example 1. Simplify each of the following. A, the square root of 81. So you want to think, what number can I multiply by itself twice to get 81? And it might not come to you as quick. It depends how familiar you are with your multiplication, your times tables. So after some thought, you realize 9 times 9 gives us 81. So our answer for this problem, it's 9. How about this one with fractions? We do the same thing. Think of the square root as a grouping symbol. So we know the square root of 16. What number can I multiply by itself twice to get 16? That's 4. And the square root of 81. What number can I multiply by itself twice to get 81? That's 9. So just like a fraction, just like a parentheses, we can go ahead and do that first. So the square root of 16 is 4. The square root of 81 is 9. And we'll talk more about radicals and special rules for them as we move on through the chapter. Example 2. Use a calculator to approximate each of the following. So some numbers are not perfect squares, meaning there is no such case where I can multiply a number by itself and get a number. For example, 13. There is no number that I can multiply by itself and get 13. For such cases, we use our calculator. Now I have this problem here for you to go ahead and take a look at your calculator. And particularly, look at the order in which you need to type in things. So the calculator I'm using makes me punch the square root button, and then I type in my numbers. So like for 13, 1, and 3, and then I get my answer. But there's other calculators where you first type in your number, so say 13, and then you apply the radical to get your answer. So look into your calculator and see which one works for you. If you're using your cell phone, usually the square root command can be found once you turn your cell phone to the side. That unlocks a lot more buttons in your calculator. So give those a try. Make sure you get these answers. Now for C, I want to emphasize, notice the negatives on the outside. Remember, that's the same thing as multiplying by, for example, a negative 1. So you just carry on the negative on the outside, just as we see the arrow pointing. Notation, radical, radicand, and radical expression. The symbol square root is called a radical. So square root applies to when you're thinking of numbers, a number that can multiply by itself twice, right? And we're working backwards for square root. But we can work with any such situation where I have a number multiplied by itself 3 times or 4 times and so on. So a square root may not be our only option. In a general sense, it's called a radical. An expression written with a radical is called a radical expression. Remember, expression is a combination of letters and numbers. So we can have something like the square root of x plus 1. This would be called a radical expression. 3. The expression written under the radical is called the radicand. So, for example, this right here is called the radicand. It's what's inside the radical. Example 3, evaluate. So, same case. Here we're taking this, for A, we're taking the square root of 100. So you want to think, what number multiplied by itself twice gives us 100? We get 10, right? 10 times 10 gives us 100. Our answer is 10. How about B? The square root of 169. So you want to think, what number multiplied by itself 2 times gives us 169? 13 works because 13 times 13 gives us 169. Simplifying square roots of a squared. First bullet point reads, a is greater or equal to 0 than the square root of a squared equals a. So meaning if this right here is positive or 0, hence the greater than, then I can just go ahead and get a in return. Notice I have an exponent of 2. 3, it is positive. If a is positive or 0, the principal square root of a squared is a. So in other words, we are looking above at the one we just worked on. What's happening is the square root and the square, in a sense, cancel each other out. What's really happening is they're mathematical opposites. They're mathematical inverses. Third bullet point. If a is less than 0, then the square root of a squared is negative a. Be careful with this one because it doesn't really translate into a problem where we work out quite as smoothly. If a is negative, the principal square root of a squared is the opposite of a. The principal square root of a squared. For any real number a, the square root of a squared equals the absolute value of a. The principal non-negative square root of a squared is the absolute value of a. So in other words, this is our disclaimer to avoid this situation where I have something squared that gives a negative. If we're working with a variable and square roots, apply an absolute value. Unless we have a statement where it says all positive real numbers or all solutions are real. Because if not, we can leave room for these cases where they're called imaginary, and those are not real numbers. So let's take a look at example A. Simplify each expression. Assume the variable can represent any real number. So here, for the first one, we have a square root and an exponent of 2. So because of this, our answer would just be y plus 3. But because we're not sure what y can be, we can always add an absolute value to ensure that we result with whatever this is, it's going to be positive. So that when I figure out what y is and I take the square root, it's going to be a positive option. Again, we do not want a situation where I'm left with a negative in the inside. So to ensure this, that's where these absolute values come in handy. Because if it so happens to be negative, the absolute value will resolve that issue. Okay, let's take a look at B. The square root of m raised to the 12th. So we'll talk about this a bit more further, but consider writing it this way. The square root of, well, we know, let's keep this in mind, we know that the square root of m to the second power will cancel out and just give us m. So let's write m to the 12th power with a lot of m squares. So m squared, we have 4, m squared, we have 6, m squared, we have 8, m squared, we have 10, m squared, we have 12. Now, each m squared will be canceled off with that radical. So how many m's do we have? That's going to cancel. We're just left with 1, 2, 3, 4, 5, 6. So our answer will be m to the 6th power. Now, what's my clever way of thinking about it? What's really happening is this square root, which we say has an index of 2 since it's a square root, it's dividing your 12 by 2. 12 divided by 2 gives us 6, just as our exponent here. But again, we'll talk about exponents as a fraction and index values soon enough. Give this one a try. Pause the video, attempt it, and then come back to it. All right. So again, we're working with the idea that the square root of x squared gives us x. So let's break it down by twos. 2, 4, 6, 8, 10. And this square root is going to cancel all these twos, so that we're just left with x to the fifth power, or the same as 10 divided by 2 gives us 5. See how that affects your exponents. Cube roots. The number c is a cube root of a, written as a cube root of a, if the third power of c is a, meaning c to the third power equals a. The cube root of a is c. So we're working with square roots, but we're not just limited with something raised to a square, right? That was our square roots. We can also have cube roots. And for those who want to think of numbers who are raised to the third power, such as 1 to the third power gives us 1, 2 raised to the third power gives us 8, 3 raised to the third power gives us, well, and if you're ever unsure, you can multiply. 3 times 3 is 9, 9 times 3 is 27, and so on. So let's take a look at these questions. Simplify. Well, actually, before that, let me leave a big disclaimer. Negatives are allowed in cube roots. For example, negative 2 raised to the third power is negative 8, because negative 2 times negative 2 times negative 2 gives us negative 8. So because we're multiplying by an odd number of times, that negative never gets multiplied out to be positive. That's why we can apply the cube roots to a negative. Take a look at this problem. A, the cube root of 27. Well, we know that for negative 27, we'll just get a negative 3. And for here, we can apply a cube root property, just like we did our square root property, where the cube root of x cubed, while the 3 and the cubic are mathematical opposites, so that we're just left with x. So our answer for this one would be negative 3x. The cube root of 8, that just gives us 2, since what number multiplied by itself gives us 8? 2 would make that a true statement. So our answer is 2. The other one's a bit tricky, but you can always play around with your calculator to make sure that you're on the right track. Well, we know that 2 cubed gives us 8, so let's throw in some decimals. Would 0.2 raised to the third power give us 0.008? And once you see in your calculator, you'll see that that holds true. So the cube root of 0.008 is 0.2. Notice, and this is not a coincidence, notice that we have a 3 and we have 3 spots to the right of a decimal. Next, the cube root of 27 over 64. This will be explained in more detail in the future, but we can apply the square roots to a fraction separately. So I can also think of this as the cube root of 27 and the cube root of 64, and apply each one separately. The cube root of 27, that's 3. The cube root of 64, that's 4. So our answer would be 3 over 4. Not bad, right? I think it's really helpful if you take the time, for example, to make yourself a list with a lot of square roots or cube roots. And then when you're working with these problems, with time, you'll become more familiar with them. Moving forward, odd and even case roots. If k is an odd natural number, then for any real number, the kth root of a raised to the k is a. So again, we're following the idea that the root and the exponent are kind of working in opposite ways mathematically, so they would undo each other. Now this is saying that we can apply a radical to any root. So let's take a look at example 6a, the fourth root of 81. So in other words, we want to think what number raised to the fourth power gives us 81. And again, it might not come right away, but maybe with some, you can practice with some numbers in your calculator, see by trial and error what works. And we see that 3 works. 3 times 3 times 3 times 3. 3 times 3 is 9, 3 times 3 is 9, 9 times 9 is 81. Cool. So our answer is 81. Let's take a look at B. The fourth root of negative 81. So I think of a number, when I multiply it by itself 4 times, I get negative 81. Well, we saw from the previous question that 3 gave us 81. So what about negative 3? Maybe you're already thinking of what's going to happen. Negative 3 times negative 3 times negative 3 times negative 3. Negative 3 times negative 3 is positive 9. Negative 3 times negative 3 is positive 9. Well, there's no such way where I can write a number to result in a negative, given that my exponent is even. Because again, if it's even, if we have an even number of negatives, they're going to multiply to be positive every single time. So because of this one, we say no real solution or no real numbers. In other words, I cannot apply an even root to a negative radicand. So this number inside cannot be negative if my small number, my index, is even. Only odds. Let's take a look at C. The fourth root of 16, m to the fourth power. Well, if we think of them separately, the fourth root of 16 and the fourth root of m to the 4, we see that these are gone, so we just get m. And for here, we get 2. Because I know 2 times itself 4 times, or we can see we get 16 in return. So our answer would be 2m. Moving on, simplifying radical expressions. For any real number a, kth root of a to the k equals the absolute value of a, when k is an even natural number. So if this is an even number, I might have to be careful and apply the absolute value. Because again, I can't be in a situation where I'm taking the square root of a negative. We use absolute value when k is even unless a is non-negative. We need to have that in our introduction, our instructions. B. The kth root of a to the k equals k when k is an odd natural number, if greater than 1. We do not use the absolute value when k is odd. So in this case, notice the main difference. I have to worry about potentially writing an absolute value when my exponent is even. If not, it's not an issue to worry about because I can take the odd root of a negative number. Example 7. For the given functions, find the indicative function values. So just as before, even with radicals, we can still evaluate. In other words, this question is just saying evaluate. Or in other words, plug in those values. So let's do that first one, f of 1. What this means, we're going to plug in a 1 for x. So that we have the square root of 4 times 1 minus 1. Let's work it out. So 4 times 1 is 4. 4 minus 1. 4 minus 1 is 3. The square root of 3, it's not a number that works out, right? There's no such number that can multiply by itself twice to get 3. So because it's not a perfect square, let's use our calculator. So by calculator, the square root of 3, we get 1.732050, and it continues on. You can round to 1 or 2 decimal places depending on what your instructions say. So let's say 2 decimal places, 1.73. That's our answer. So we can say something like f of 1 equals 1.73. All right, let's go ahead and do f of 6. F of 6, the square root of 4. Instead of x, we're going to write 6 minus 1. All right, 4 times 6 is 24. 24 minus 1 gives us 23. 23 is not a perfect square, so we have to use our calculator. The square root of 23 gives us 4.795831, and it continues on forever. If we round, that's about 4.80 if we round to 2 decimal places. So our answer is f of 6 is 4.80. Last one, f of 0. So this just means we're going to plug in 0 for x. So that we have the square root of 4 times 0 minus 1. 4 times 0 is 0. 0 minus 1 is negative 1. So for this one, our answer is not a real number, not a real solution. And that's okay for now. Example 8. Graph g of x equals the square root of x plus 3. So these radical functions, because I can't take the square root of a negative, the parent function, say g of x equals the square root of x, looks like this. It starts at 0, so I could take the square root of 0, and it kind of has this figure here. So this is our parent function. So if we have a square root function, it's going to look something like this. Now, as we have shifts in our function, we can move it up, down, left to right, flip it over, right? We can have all these different, what are called transformations. So let's go ahead and see how our graph from our question, g of x equals the square root of x plus 3, how it affects our problem. Let's figure out some test points. All right, so we're trying to work with the square root of x plus 3. What should we pick for x? Well, we for sure do not want to work with numbers that would make the inside or radicand negative. So what numbers are we allowed to work? Figure out what your domain is. What's the domain? What values for x work for the square root of x plus 3? To find your domain, you're going to set your inside, x plus 3, set it to greater or equal to 0. Why greater or equal to 0? Because you want the inside to be greater. You want it to be positive. Equal to 0 because 0 is okay. Keep in mind that the square root of 0 is 0. Because 0 squared gives us 0. 0 times 0 is 0. 0 is okay. All right, let's go ahead and work it out. Let's move the 3. Move the 3. X is greater or equal to negative 3. So I'm saying that x can be any number that's 3, negative 3, or bigger. So I can work with negative 3. What's bigger than negative 3? Negative 2. Draw a number line in case you need to think about it a bit more. Negative 3, negative 2, negative 1, 0, 1, 2, and so on. Let's go ahead and work these numbers out into our function. Let's go ahead and plug them in for x. So the square root of negative 3 plus 3, we get the square root of 0, we get 0. The square root of negative 2 plus 3, we get 1. The square root of 1 is 1. The square root of negative 1 plus 3 is 2. The square root of 2, it's not a perfect square, but we can use our calculator to help us out. That's about 1.4. And the square root of 0 plus 3 is square root of 3, which is, we have to use our calculator again. It's about 1.7. And let's do one more for good measure. Let's do 1. The square root of 1 plus 3 gives us 4. The square root of 4 is 2. So now we have some points we can plot. We have negative 3 and 0, negative 2 and 1, negative 1 and 1.4, 0 and 1.7, and 1 comma 2. Let's go ahead and plot them in our Cartesian plane. Always label your x and y axis and number them. So it looks like we just need to go up to 4, up to 3, right? Let's draw 4 tick marks in each one. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. All right, let's go ahead and plot these points. I have negative 3, comma 0, right? Negative 3, comma 0. Negative 2, comma 1. Negative 2 up 1. Negative 1 up 1.4, so 1.5 almost. 0 and 1.7, it's almost 2, and I have 1 comma 2. And we see that our graph can continue on as our x's get bigger, but it does not get any lower than negative 3, right? So that doesn't happen. So here we have our graph, the square root of x plus 3. And notice how it resembles our parent function for radicals, right? That was our parent function. So when we're dealing with square roots, it's always going to look something like that. It's very important, it's very crucial that we take a moment to find this initial point, which is the first number that we start off with, because that lets you know where it starts and where it branches out to. Okay, this was section 6.1, radical expressions and functions. Thank you.